In this video, we're going to look at something called line integrals, in particular scalar line integrals in the plane. These line integrals give us another class of integral to work with. And as we've been working through 1 dimensions to 2 dimensions and now to 3 dimensions, we've kept adapting our integrations to be over regions in the real number line in R1, to regions over an area in R2, to regions over a volume in R3. And another type of integral we can use is just the line integral. Now keep in mind that a line can be straight or curved, and these integrals play a significant role in vector calculus. We can use them to integrate both scalar valued functions and vector fields along a curve. So why do I care about a new class of integrals? If I recall in the past that my integration was giving me information about areas and volumes bounded by curves, but I might need to know about a path along a surface or volume rather than about an area or volume of a region. The path of the Voyager deep space probe actually depends on being able to use line integrals. It depends on being able to know where that probe is with respect to the influence of a gravitational field exerted by planets like Jupiter or Saturn that will allow them to use that gravitational field to slingshot Voyager further on its path to the outer parts of the solar system. No one who planned this route for Voyager is interested in an area or volume. They are interested at what is happening along the path itself. Now there are several types of line integrals I may end up working with, and we need to be able to identify which kind we need to use for a particular problem. There are scalar line integrals in a plane, there are line integrals for vector fields, there are work integrals, and there are circulation and flux of vector fields. What we're going to see as we work through these types of line integrals is the basic form and the process is really going to be the same, but the context of the problem actually gives us the information about what we're working with. So when I'm working with scalar line integrals in a plane, I want a line integral of a scalar valued function over a curve in a plane that involve a surface given by z is equal to f of xy and a parameterized curve C that lies in the xy plane. To begin with, I'm going to assume that f of xy is greater than or equal to 0 for all xy on the curve, but I don't have to limit myself. It just makes it easier to set up the things we're going to use. The first thing I'm going to plot is a surface in a 3D space. I have a surface that isn't necessarily a flat plane that intersects my z-axis but lies above the xy plane. There is a parameterized curve C of S that lies in the xy plane. There is the surface that I've mapped that is defined by z is equal to f of xy. So imagine that I can create a curtain-like surface that is formed of all the line segments that run from my curve C in the xy plane to intersect with the surface z is equal to f of xy. And I want to find the area of one side of the curtain in terms of a line integral. I can always divide my curtain into n partitions that are each not more than delta wide, and then sum them all up in a Riemann sum, and then I take the limit as I let delta go to 0 and the number of partitions go to infinity in order to get an integral. So I want to look at a scalar line integral in a plane where I use arc length as my parameter. Let's suppose that my vector valued function f is defined on the smooth curve C that's given by the vector r of s is equal to a vector with components x of s, y of s that is parameterized by the arc length s. And the line integral of f over c is given by the integral over c of f of x of s, y of s ds, which can be expressed as the limit as delta goes to 0 of the sum from k equal 1 to n of f of x of s sub k star y sub k star times delta x sub k. Now, provided the limit exists over all partitions of C, this is true. When this limit does exist, f is said to be integrable on C. There are other more compact notations for this that you may see. You may see an integral over C of f of r of s ds. You may see it expressed as the integral over C of f of x y ds. Or you may simply see it written as the integral over C of f ds. All of these give me the length of the curve over C. Let's work an example. I want to evaluate the given line integral with arc length as the parameter. My line integral is the integral over C of x plus y ds. C is the circle of radius 1 centered at the origin 0, 0. The first thing I need to do is parameterize this curve C using the arc length S. I know that C is a circle of radius 1 with a center at 0, 0, and it lies in the xy plane. This means that C can be expressed as x squared plus y squared is equal to 1, or by r squared is equal to 1, where r is equal to 1. I also know that x is equal to r cosine theta gives me x is equal to cosine s when my r is equal to 1, and my parameter s is used in place of theta. Y is equal to r sine theta can also be written as y is equal to sine s, again using r is equal to 1 and s for theta as my parameter. This parameterization allows me to write my line integral as an ordinary integral from 0 to 2 pi of the quantity cosine of s plus sine of s ds. This gives me negative sine s plus cosine s evaluated from 0 to 2 pi, which gives me 0 plus 1 minus 0 plus 1, or 0. Now, I can use things other than arc length for my parameters, and it's important to know whether or not I'm working with arc length or some other parameter when I'm working with these integrals. For curves that are easy to parameterize with arc length, it's wonderful. But not all of my integrals will give me easy access to using arc length as a parameter. Sometimes we're given a parameter like t, and this is not an arc length. So we need to be able to use a change of variables to make my integration work out. So if I need to evaluate a scalar line integral in R2 with a parameterization that is not arc length, I need to let f be continuous on a region containing a smooth curve C that is defined by the vector r of t is equal to a vector with the components x of t, y of t, where a is less than or equal to t, which is less than or equal to b. When this happens, then my integral over C of f ds becomes the ordinary integral from a to b of f of x of t, y of t times the magnitude of the derivative of my r vector dt. This gives me an ordinary integral from a to b of f of x of t, y of t times the square root of the quantity x prime of t squared plus y prime of t squared dt. Now, we need a process for evaluating these line integrals over a region C for FDS. The first thing we want to do is find a parametric description for my curve C that is in the form of r of t is equal to the vector x of t, y of t, where a is less than or equal to t, which is less than or equal to b. Then I want to compute the absolute value of r prime of t. This is the magnitude of the derivative of my r vector. This is equal to the square root of the quantity x prime of t squared plus y prime of t squared. Now I want to make substitutions for x and y in the integrand in terms of my parameter t, which will allow me to evaluate an ordinary integral, so that my integral over c of f ds is equal to the integral from a to b of f of x of t, y of t times the magnitude of the derivative of r of t dt. So let's work an example. I want to find a parametric description for C in the form r of t is equal to a vector with components x of t, y of t. I want to evaluate the magnitude of the derivative of r of t and then convert my line integral to an ordinary integral with respect to the parameter and evaluate it. The line integral over c that I'm given is the integral over c of the quantity x squared plus y squared ds, where c is the line segment from the point 0, 0 to the point 5, 5. The first thing I need to do is find a parametric description for c in terms of the parameter t. I'm going to use the equation for writing r of t as a linear function that we learned in prior work in calculus. R of t is given by the vector x sub naught y sub naught plus t times the vector ab, where the vector ab is the vector between the 2 points. When I use this with my point 0, 0 to 5, 5, I get y is equal to x becomes a vector with coordinates 5t, 5t, where 0 is less than or equal to t, which is less than or equal to 1. My magnitude of r prime of t is given by the square root of 5 squared plus 5 squared, which is equal to 5 times the square root of 2. So that my line integral over c of the quantity x squared plus y squared ds becomes the ordinary integral from 0 to 1 of the quantity 25t squared plus 25t squared times 5 times the square root of 2 dt. This is a fairly straightforward integral to perform. I simply combine my like terms. I'm taking the integral from 0 to 1 of the quantity 50t squared times 5 times the square root of 2 dt. This gives me 250 times the square root of 2 over 3 t cubed evaluated from 0 to 1, which reduces to 250 times the square root of 2 divided by 3. So now you get to try it. Pause the video and find a parametric description for c in the form of r of t is equal to the vector with components x of t, y of t. Then evaluate the magnitude of r prime of t and convert the line integral to an ordinary integral with respect to the parameter t and evaluate it. When you're ready, restart the video to check your understanding. The line integral you need to evaluate is the integral over c of the product xy raised to the 1/3 power ds, where c is the curve y is equal to x squared and 0 is less than or equal to x, which is less than or equal to 1. The first thing I need to do here is find a parametric description for c in terms of the parameter t. Y is equal to x squared is a region between 0 and 1 that takes an input value and squares it. If I use t as my input value, y is equal to x squared will give me a vector with components t and t squared, where 0 is less than or equal to t, which is less than or equal to 1. The magnitude of r prime is given by the square root of 1 plus 4t squared, so that my line integral over c of f ds is equal to the integral from 0 to 1 of t cubed raised to the 1/3 power times the square root of 1 plus 4t squared dt. This simplifies to the integral from 0 to 1 of t times the square root of the quantity 1 plus 4t squared dt. Now I'm going to use a u substitution where u is equal to 1 plus 4t squared, which means that du divided by 8 is equal to t dt. This gives me an integral that is equal to the integral from 1 to 5 of u to the 1/2 over 8 du is equal to 5 square root of 5 minus 1 over 12. Pay attention to the fact that I did have to change my limits of integration with that substitution. This is how we work with scalar line integrals in a plane in space. Be sure and let me know if you have any questions.